Over the past few years, we've seen a huge shift in storage, going from these big clunky mechanical hard drives to these sleek, compact SSDs. SSDs are smaller, lighter, and way faster. How do SSDs actually work? What makes them so much tinier, lighter, and faster than traditional hard drives? Smash that like and subscribe button. Let's get started. Here we have an electron, and in front of it, a wall made of insulating material. Now, common sense tells us there is no way this electron should be able to get through that wall. But here is the thing. At the microscopic level, a lot of what we think we know about how the world works kind of goes out the window. Under normal conditions, the odds of this electron somehow tunneling through that wall are incredibly slim. But if we crank up the electric field high enough, suddenly the odds shoot way up. This phenomenon is called quantum tunneling. So here is the cool part. We can actually use this phenomenon to build something useful. Let us start with a conductor. In real manufacturing, this is usually made of polysilicon. Then, we wrap the whole thing in a layer of insulator. Now, under normal conditions, electrons cannot get through that outer layer. But when we hit it with a strong electric field, something wild happens. The electrons quantum tunnel straight through the insulator and pile up inside the conductor. And once those electrons are in, they basically stuck. Even if you completely cut the power, they can stay trapped in there for around 10 years. Now, when we want to wipe them out, just flip the electric field in the opposite direction, and the trapped electrons get pulled right back out. So with this setup, we can store information for the long haul, even without any power, and this brilliant little structure, we call it the floating gate. Of course, the floating gate by itself, not enough to build an SSD. We need one more key player. This is a transistor. The base here is made of P-type semiconductor, and these two little ears on top are N-type semiconductor. Now here is the thing. P-type conducts electricity, and also conducts electricity, but right where the P-type and N-type meet, they form what is called a p-n junction. And this junction is not conducted. So basically, these two N-type ears are electrically cut off from each other. No connection. Alright, check out the middle section here. We have got an insulating layer, a metal electrode on top, and another electrode underneath the whole thing. Now let us do something. We are going to pump 5 volts into the top electrode and keep the bottom one at 0. This creates an electric field inside the transistor pointing from top to bottom. But wait for it. Electrons are negatively charged, so a whole bunch of electrons get yanked upward toward the top of the transistor. And because of that, a tiny conductive channel forms right there, and the two N-type semiconductors become connected. So the top electrode, we call it the gate, and the bottom one, that is the substrate. Here is the deal. By playing around with the voltage on these two electrodes, we can basically flip the connection between those two N-type pieces on and off, like a light switch. This is the workhorse of modern computers, the legendary MOS transistor. Alright, so we have got our floating gate, and we have got our MOS transistor. We are going to tuck that floating gate right underneath the gate of the MOS transistor. It looks something like this. This is what we call the floating gate transistor. So here is the million-dollar question. How on earth does this thing actually store data? We crank the gate up to 20 volts and keep the substrate at 0 volts. That voltage difference creates a crazy strong electric field. A whole bunch of electrons tunnel right on in and get stuck in the floating gate. Now, what if we want to wipe the data? Flip it around 0 volts on the gate, 20 volts on the substrate. Now the electric field goes the other way, and those trapped electrons, they get pulled right back out. And that is how a floating gate transistor writes data and erases it. Alright, so we have got writing covered, we have got erasing covered. But there is one more thing we absolutely need, and that is reading the data basically. We need to figure out how many electrons are actually hanging out in that floating gate. So if there are 0 electrons in the floating gate, this whole thing acts just like a regular MOS transistor. When we crank the gate voltage above a certain point, say 5 volts, conductive channel forms and those two N-type pieces connect. If the voltage is below 5 volts, not enough electrons to build that channel. The two N-type pieces stay separated, no connection, and that magic number, that 5 volt mark, That is what we call the threshold voltage. But here is where it gets interesting. When electrons are trapped in that floating gate, remember, electrons carry a negative charge, and that negative charge, it actually cancels out some of the voltage coming from the gate. So by the time the voltage finally reaches the channel, it is already dropped below 5 volts result. Those two N-type pieces, still disconnected, no current flows. And that is how we read the data. We basically test it against that threshold voltage we talked about. No electrons in the floating gate. The transistor conducts current flows. Electrons in the floating gate. Same voltage? Nope. Nothing. Now here is how we think about it. When it conducts, we say this floating gate transistor is storing a 1. That means 0 electrons inside. When it isn't T-conduct, that is a 0. That means electrons are stored in there. So here is the rule to remember. 0 means electrons are stored. 1 means they are not. I know. It feels a little backwards at first, but once it clicks, it sticks. Here is the thing. One floating gate transistor. It only knows 2 states, 0 or 1, just one single bit of data. And this type, we call it SLC, which stands for single level cell. Now, SLC is awesome because it is simple. Simple logic means it is fast and super reliable, but there is a trade-off, lower information density translation. It costs more to store the same amount of data, and that is why the big manufacturers did not stop there. They started figuring out how the heck can we make these floating gate transistors store more data. Alright, so in SLC we had it pretty simple. No electrons equals 1, lots of electrons equals 0. What if we get a little more creative? So check this out. 0 electrons could represent 1, 1. A few more electrons, that is 1, 0. Even more 0, 1. And if we pile in a whole bunch, that is 0, 0. Suddenly one floating gate transistor can hold 4 different states. That is 2 bits of data. And that drops the cost way down. A floating gate transistor that storing 2 bits this way, we call it MLC multi-level cell. But hold on, nothing's perfect, right? With SLC, reading data is dead simple. We just do one threshold check and we are done. MLC, oh man, it needs several. And writing, that is where MLC gets really messy. Check this out. It starts with a lower write voltage. Then it pauses to read and see if enough electrons are in there. If not, it cranks the voltage up a tiny bit, writes again, then reads again. And this whole dance, it repeats several times until finally, the floating gate has enough electrons. So yeah, MLC is significantly slower than SLC, reading and writing both. But here is the thing. Cost is king, and MLC saves some serious cash. So is it worth the trade-off? Honestly, for most people, yeah, it is. And it does not stop there. In recent years, we have seen even more types pop up. First came TLC, that is triple-level cell, stores 3 bits of data. Then QLC quad-level cell, 4 bits. Yep, you heard that right. Same deal as before, just taking the logic even further. TLC and QLC, they push the density even higher and drive the cost even lower. But you already know where this is going, right? More bits, more complexity, more complexity. Slower reads, slower writes. It is always a trade-off. Always. One floating gate transistor, clearly not enough. That is why in real SSDs, we hook them up into big old arrays. But first, let me show you the old school way, the 2D planar array. So here is how it works. We arrange the floating gate transistors in columns. And here is the smart part. Each pair of transistors actually shares an N-type semiconductor. In other words, these transistors are all connected in series. And the circuit diagram, it looks something like this. Now check this out. This right here is a NAND gate circuit. See these two MOS transistors connected to ground. They are in series, just like our floating gate array. And that, my friends, is exactly why we call this whole setup NAND flash. So NAND literally stands for not and. That is just how the logic works. And fun fact, the guy who invented this, his name is Fujio Masuoka, from Toshiba. And here is the story. He thought this technology had lightning-fast speed, so he named it NAND flash. Pretty cool, right? Alright, back to the NAND array. So these floating gate transistors connected in series. We call this whole thing a string. Now at the front and back of this string, we have got 2 regular MOS transistors. Think of them like switches. The one at the front is called the string select transistor, and the one at the back, that is the ground select transistor. At the front of the string, we extend a wire. This is called the bit line, and at the back, another wire. This one goes straight to ground. Now here is the cool part. We copy this string horizontally, row after row, and we have got ourselves an array. Oh, and one important detail. This entire array shares a single substrate, and that is why we call this whole thing a block. One shared substrate phi1 block. Next up, we take the gates of all the string select transistors and connect them horizontally. This line right here, that is called the string select line. The same deal for the ground select transistors. Connect all their gates together and we get the ground select line. Now, for the middle section, we run a few horizontal lines to connect all the floating gate gates together. These are called word lines. And here is a key concept. The row of floating gate transistors connected by a single word line. That is what we call a page. And there you have it, a complete 2D NAND storage array. Beautiful, isn't it? So how does this whole storage array actually work? Let us start with the read operation. Now, a single read operation can only read one page of data at a time. So let us say we want to read this page right here. First step, we pump a high voltage into both the string select line and the ground select line. That turns both of them on like flipping two switches. Next, we apply a voltage to all the other word lines, the ones we are not reading. Let's say 10 volts. Now you might be wondering, why 10 volts? We know that when electrons are sitting in the floating gate, they cancel out some of the gate voltage. And that means the threshold voltage, the amount needed to actually turn the transistor on, goes up. So here is the deal with that 10 volts we talked about. It is high enough to force every transistor to turn on, even the ones with their floating gates packed full of electrons. But at the same time, it is not so high that it would accidentally trigger quantum tunneling. It is a sweet spot. So once we apply that 10 volts, every single floating gate transistor on those word lines goes into conducting mode. And from the circuit's perspective, we can basically treat them all as just wires. Next, we hit the word line of the page we actually want to read with the threshold voltage. And here is where it all comes together. Floating gate has electrons, transistors off. Floating gate has no electrons, transistors on, current flows. So the only thing left to do, check whether each bit line is connected to ground. That tells us everything. We can instantly tell what state each transistor is in, and all the data we wanted, right there on those bit lines. Now, those bit lines do not just hang there. They all feed into something called a page buffer. Think of it like a waiting room. The data chills here for a split second, then gets shipped off to memory or wherever it needs to go. Smooth. So how do we write data? Let us say we want to write to this page right here. Step 1. We crank the string select line up to a high voltage. That flips all the string select transistors on. Step 2. We drop the ground select line down low. That shuts all the ground select transistors off. We also set the bit line voltage to 0. Now here is where it looks familiar. Just like when we were reading, we pump 10 volts into all the other word lines. That turns all those floating gate transistors on, and basically turns them into wires. After that, we hit the floating gate with a high voltage to pull electrons in. Let's walk through an example. Say we want to write a 0 to the first floating gate transistor on this page. That means we need to store electrons in it. So we crank up the voltage on that word line high enough to trigger tunneling. Something like 20 volts, and electrons tunnel right into the floating gate. Right operation, done. But here is the problem. This word line does not just connect to one transistor, it spans the entire page. Every single floating gate transistor on this page gets hit with that 20 volts, which means they all pull electrons in. Yeah, that is definitely not what we want. We only wanted to write to one of them, not the whole row. So how do we fix this? How do we target just one specific transistor? Here is the trick. So let us say for the second transistor on this page, we do not want it to absorb electrons. What do? We crank up the voltage on that bit line, bump it up to something like 8 volts. Now remember at the start of the write operation, we turn the string select transistor on and the ground select transistor off. That means no complete circuit, right? So here is what happens. That 8 volts applied to the bit line. It is basically trapped. It sits there, stuck along the entire string. Every single point on this string will have 8 volts. Now, let us look at the specific transistor we are targeting. Its gate has 20 volts, and the channel below has 8 volts. When these two voltages cancel each other out, the net voltage acting on the floating gate is just 12 volts, which isn't T enough to trigger tunneling. So no electrons get pulled into the floating gate. Here is the rule: want electrons to be absorbed. Apply 0 volts to the bit line. Do not want electrons to be absorbed. Apply 8 volts to the bit line. This technique is called channel inhibition. However, this method requires very high voltages, so it is gradually falling out of use. These days, manufacturers use a different technique called channel self-boosting. It leverages the natural parasitic capacitance between floating gate transistors to inhibit the channel, but this method is much more complex in principle. So we'll skip the detailed explanation here. Alright, now the erase operation. This one way simpler. To erase a floating gate transistor, we apply a sufficiently high voltage to the substrate, which pulls all the electrons out of the floating gate. For our array, it is the same thing. Just apply a high voltage to the substrate. But here is the thing. Since this block shares a single substrate, erasing will wipe out all the floating gate transistors on the entire block at once. And that is the 2D NAND flash array for you. As time went on, consumer demand for storage kept climbing, and 2D arrays, they started hitting their limits. So the big manufacturers got to work, looking for the next breakthrough, and that is when 3D NAND arrays were born, the third dimension. Alright, here is where it gets visual. Let us focus on a single string from a 2D array. Look closely. Now, we're gonna spin it around. Watch as this flat structure transforms into a pillar. Okay, here is the thing. The internal structure. It doesn't actually change at all. Check it out. Top of the pillar, the string select MOS transistor. Bottom, the ground select MOS transistor. And right in the middle, the floating gate transistors. The only difference, these floating gate transistors went from a flat layout to a wrapped around structure. Now, if we stack up multiple pillars, we can form a 3D array. At the top of the array, each string has a bit line extending out. We connect these bit lines vertically. Every string has a string select MOS transistor at its head. We connect these string select transistors horizontally. This is the string select line we mentioned earlier. Whichever string select line has a high voltage applied, its corresponding bit line gets connected to that string. In other words, the string select line acts as a bit line selector. And for the floating gate transistors below, we connect them horizontally too. These are exactly the word lines we mentioned earlier. Do not forget the ground select MOS transistors at the very bottom. They also need to be connected, forming the ground select line. And there you have it, the 3D NAND array. This is one string. This is one page. The ones on top are the bit lines. And the ones on the side are the word lines. NAND flash is a sector that is still rapidly evolving in the semiconductor industry. Over the past decade, we've seen some insane growth. Technology keeps getting better, and prices they keep dropping. Along the way, some manufacturers just couldn't keep up. They fell by the wayside. Others, they held strong. And then there are the new kids on the block, the rising players shaking things up. So here is what I want to break down next. How has NAND flash technology transformed over the years? How did Samsung pull off replacing the floating gate layer and earn the nickname King of Punching Holes? Why did Intel, of all companies, end up getting left behind and booted out of the SSD market? And how did Yangtze Memory, this total newcomer, manage to claw its way into the game? It is a wild story, and I've got it all lined up for you. So what do you say? Hit that subscribe button and let's dive in together. I'll see you in the next one.